faculty who are interested in research and education in the aerosol science and engineering arena. Of course, the word aerosol sometimes is misunderstood by many people. Till this COVID situation took place, people thought it was things out of a spray can. The good news is now there's a little broader understanding, but as my colleagues say, the bad news might be that they'll only associate this with the coronavirus going forward. It is much broader, and I would encourage you to look up the website for Center for Aerosol Science and Engineering at Washington University to learn about the diverse applicability of this fascinating field. Today, though, we will be talking about the COVID-19 situation. There are several, I'll just put a caveat, there are several other individuals who are not going to speak today who are also doing work in this arena at Washington University through CASE, and the website would have some of those details too. And I'll just introduce briefly by name the speakers, and each of them will come on later on. Rajan Chakravarti will speak on models to predict the spread in larger populations. Richard Axelbaum on guidance to frontline healthcare physicians and healthcare workers on respiratory protection. Brent Williams on some details on characterizing these face mask filters in the laboratory. And then if time permits, I'll talk about a little bit of antiviral drug work that we are doing. So in terms of some housekeeping rules, because we have a large group here, I think it's a really large number, and thank you again for listening in. The students, there are some students who are doing this as part of a class. For them, there's a short quiz that will come on around 11:20 or so and be open till noon, so please partake of that quiz. For others and everyone else, including the students, I request you to be on mute, and we will speak one after the other. And please, as you have a question, type it into the chat session. Those who are not familiar with Zoom, there is a chat box. You can type in your questions. And at the end, we want to have a discussion and maybe even individually answer these questions. And just because of the large number, exceeding now 170 people, I think, please use the chat box as we are presenting, so you don't forget your question, and also saves us time at the end. Okay, so each of us will speak for about 10 minutes, and at the end, we will have a discussion session. So with that, let's just get started. I'll lead off the presentations, and I'm trying to see, okay. Can you see the screen? Is it? Yeah, these technical issues are always problematic. So let me, hey, Sungyun, can you, okay, let's see. Okay, great, you can see now. Thank you. I hope everyone can see the screen.
Yes, yes, we can.
Great, so I'll be talking about the airborne transport of the SARS-CoV-2 virus. And in our lab, there are many projects underway. I'm going to focus on airborne transport, and the PhD students should be getting all the credit. They do all the fascinating work, have the brilliant ideas, and I'm just presenting on behalf of them here. So if you look at this in terms of modes of transmission of the SARS virus, SARS-CoV-2 virus, it is indeed fascinating. As I'm talking, I'm also breathing. I'm getting a little excited. It's an exciting topic to be discussing. I'm giving out aerosols, right? Just as a normal individual. If I cough, I will give out, as indicated there qualitatively, maybe a larger number of aerosols. If I sneeze, the same. And both, if an individual is symptomatic, which means they are carrying a higher loading of the virus and have symptoms of cough, sneezing, and things like that, or even if I'm asymptomatic, then this is happening as we are all sitting and listening to this. Now, these aerosols, as I said, aerosols are just small particles suspended in air, right? In this case, these would be little droplets. And if you look at this, the spread could happen by direct contact. So the aerosols that are droplets that are actually emitted by these individuals might go and deposit on a surface, right? And then sometime later, you might touch the surface. That is the indirect mode coming from surfaces. But there could be a direct contact methodology. If I shake your hands or if you kiss your girlfriend, you're going to pick up these viruses. And of course, today's topic is airborne transmission as aerosols. And this aerosol eventually might be inhaled by another individual and then deposit in the lung. And there is a size-dependent deposition efficiency in our respiratory system. It's rather interesting. It acts in some sense what happens in a filter too, and we'll be talking about filters later. So particles of different sizes will deposit at different regions of the respiratory system and with different efficiencies. And you breathe things out. Things that don't deposit will actually be emitted back into the atmosphere. So there are important considerations. The virus firstly has to be emitted, right? The virus has to enter the respiratory tract, and it has to remain viable and replicate in the system so as to cause an infection. So these are all important in eventually picking up an infection. So this is now a little more detail. You see the picture of an individual, and I have blown up the droplets. The droplets are not as big as someone's head, but just so that you can see it. On the right is what we call a size distribution, the number concentration as a function of particle diameter. So you can pick your favorite particle diameter, go up onto this curve and find out how many particles are in that size range, right? And of course, this, I just showed it as a U-shaped curve, inverted U-shaped curve. Different particle sizes are present in different concentrations. And this could represent the distribution of the droplets that we actually emit into the air around us. And this is now quantitative data. So if you look at the literature, as I said, when I'm speaking and breathing, I have a certain concentration, I have a geometric mean size, and there's a distribution of these particle sizes. So one can get quantitative information like this as to what is coming out. Let's look at a little more detail as to what's in one of these droplets. And I just pick a 10 micrometer size droplet. That's typical. It's about the mean size of if I'm breathing out or coughing. And in this droplet will be these viral particles. There will also be some mucus or salt, as I might call it, dissolved in the droplet. And as this then I look at, of great interest to me is the specific virus. If it happens to be contained in these droplets, they have a rather interesting structure. This unit, and this is not to scale, I'm just blowing up the picture so you can get a good look at it. The viral particle is about 120 nanometers. So compared to that droplet, this is very tiny. It's in the nanometer size ranges. 1 nanometer is 1,000th of a micrometer. And just so that you know, if you feel hair on your head, that is about 50 micrometers in diameter. Okay, let's dig in a little further. This virus has a certain structure, and it's rather interesting because some of these proteins, there are three major types of proteins. They are assembled in a certain way, right? And of great interest is the protein structure in the interior, because that's the one which will replicate. Also of great interest are the spike-like structures in the outside. And that's why it gets its name. It looks like a crown, and it's called the coronavirus. This is extremely important because when it is in the lung, it is used to sort of connect to the cells and enter the cells. And I'll talk a little about it. So there are four major things of importance. One is this nanoparticle, as we refer to it, or the aerosol now. It has entered my respiratory tract. It has to bind and fuse. And it's these mushroom-shaped spikes that help do that. Once it enters the cell, it has to replicate. This virus is problematic because it has a self-correcting mechanism. And some of these are all particle mechanistic details like particle physics that many of the aerosol scientists study, and we can use to study these. And ultimately, when it has replicated, the human system will try to shed it, and I will release it back into the atmosphere through those cough, breathing, talking, and then it spreads, right? It, of course, has to remain what we call as virulent or infective, so that when it's outside the cell and I or someone inhales it, they will pick up the infection. Just to show you a little more, we are good at understanding particle transport. So now you bring in equations. I won't go into those details, but I'm just showing you certain characteristic times. So the settling time is shown in the red, and the evaporation time. You know, this droplet, if it is large, it'll settle fast and it becomes a surface problem. But as the droplet is released, it also evaporates. So you can see that the evaporation time for 100 micrometer droplet is much smaller than that of the settling time. So we have to take that into account. So this is the current work that we are doing, trying to understand the spread and go into detail. So I'll just show you some results. 100 micrometer particle, if I ignore evaporation, it'll travel for about 2 meters. Remember, the 2 meters is like the 6 feet separation, right? This can help us find out how far I need to distance myself. It stays afloat for about 5 seconds. If I account for evaporation, it doubles the distance. It increases the time significantly. If the droplet happens to be 10 micrometers, you can study that. Now, if I take evaporation of a 10 micrometer droplet, it says it will go for 50 meters. So it has a very long lifetime, but obviously it might be intercepted by something else in the meantime and so forth. So these are just some estimates that one can look at. Finally, I really want to collect data. I just wanted to mention that we also design sensors to measure these things. And I'm showing you here a miniaturized particle counter. The student is wearing it on her lab coat. We want to actually deploy these in patient rooms so that we can get the data. And here's some very preliminary data, literally hot off the press. And you can see if the number of patients go up, maybe the concentrations go up. This is the total particle count in the waiting room, because these patients are often coughing and sneezing. Of course, they have some kind of protection, but you can also see the problematic aspects to other people who might be in the room, including the healthcare physicians and so forth. So we are studying this. We also want to make sure what fraction of those particles actually contain the virus. And we hope to someday deploy this instrument, which we have in our lab. It's a little larger compared to the samplers, and it'll tell us the exact concentrations of the SARS-CoV-2 virus that is airborne. So I just gave a quick brief overview. We will now switch to the next speaker, Dr. Chakrabarty. So Rajan, you can take over.
Yes, hello everyone. Can you hear me? Pratim, am I audible?
Yes, yeah, perfect.
Okay, thank you, Pratim, for a very nice and a comprehensive introduction. Carrying on from where Pratim left off, he explained the dynamics of how aerosol droplets are transmitted or to different individuals. So what we were interested in is at the outbreak of COVID, how do you predict the spread of this virus in different populations. So I have to give all the credit, as we always do, as the PI, to my team, Peyton Beeler, who is a second-year PhD student, and Pai Lu, who are the real workhorses. And special thanks and shout out to Vince Rupert, who is the IT support staff, who has been helping us with a lot of these outreach activities, and also a lot of Dean staff members too. Slide change, please. So Pratim, can you change the slide?
Always something goes wrong. Let me see. 1 second. I think every time there's a little bug in.
Okay.
You can keep speaking. I'll do it in a second.
Okay, so to start off, the following slide you will see, since this is targeted to our graduate students, I want to connect aerosols and the spread of this virus in populations. Specifically, we have seen in all the different classes being offered at the graduate level how aerosols are formed. In this particular case, we are taking the example of soot, and soot has an aggregate structure. We see that it starts with a single particle, and then it interacts with a bunch of other particles to form different aggregate structures depending on the size of interest. So, the entry point to understanding the spread of this virus in the population is what we call it as an aggregation kernel. So what the aggregation kernel is, a single droplet, how many other droplets it interacts with, and with what probability. So initially, if you have a very dilute system of aerosols, a single particle only interacts with one single particle. We call it the binary kernel. And the probability that they stick is very high. Now, as you go on densifying this aerosol system, you get the probability that one aggregate or a bunch of other particles interacts with another group of particles. It goes on increasing, and that is controlled by this lambda factor. So in typical aerosol systems, you have lambda equal to 0. In dilute systems, that's why you have what we call is a constant kernel. As you go on making jellos and very highly dense aerosol structures, you have lambda greater than 1. So this is the kernel. A slide change, please. So this is very similar to how aerosols, how this COVID-19 has been spreading in different populations. So you have here the generation scheme. One infected person could infect 3 other or more than 3 people, and then it multiplies exponentially. It grows. So first thing to fix is what we call is the kernel. So this kernel for epidemic spread, the analogous to the aerosol kernel, we have a number known as a reproductive number R0. So what is this reproductive number? It's the number of secondary infections that one infected person would produce in the fully susceptible population through the entire duration of the infectious period. And typically when this started out in Wuhan, this R0 was determined to be close to 3. That is, and I'll explain what goes on in this kernel. Slide change, please. Okay, so R0 here is the product of the number of contacts per unit time, probability of transmission per contact times the duration of infection times the probability of surviving exposed stage. So you might be thinking in terms of a flu, what is the R0? Well, R0 is typically less than unity, means that it has very low probability, and the number of contacts per unit time is also very low. So, and if the R naught is less than unity, it implies that it is not going to be an epidemic. But in case of epidemics like COVID-19, SARS, MERS, you have typically R naught greater than unity, which implies that the equilibrium point is unstable and the disease is going to spread. Slide change. So once we figured out the R naught, now we integrate that into a model. The most reliable and the most common model for understanding the spread is what we call it as a susceptible, exposed, infectious, recovered model, or the SEER model. So it is essentially a bunch of integral differential equations similar to the Smolokowski's equation, where you have a gain term and a loss term. So a loss term in this case implies recovered or death of a person. So we set this model up, but the beauty of a SEER model is you can also integrate additional constraints, such as asymptomatic individuals, social structure, age, and so on and so forth. So slide change. So when we initially started out, we wanted to find out what is the effect of mobility. So this was the phase when social distancing was not being implemented. So the phase between March 1st through March 15th, I would say. So we had a mobility network-driven dynamics integrated into our SEER model. Slide change, please. And eventually, what we had was, upon the enforcement of social distancing, we also integrated what we call as the social interaction dynamics metapopulation scheme, where we take into account what is the daily time of exposure between people in different age groups amongst themselves. And so when you have a matrix like this, you can really reduce the interaction time depending on what effect would social distancing bring about. Slide change, please. So with all these different dynamics, and it is much more complicated, but you can go and visit this website. We have set this up, and it is accessible through my faculty webpage in the McKelvey School. We do a very comprehensive forecast, and the thing what we are doing, which is different from the other models, is we connect the epidemiological parameters to the medical demands, in this case, hospital and ICU beds availability, and what is the effect of social distancing in balancing or reducing the medical demand to supply ratio. Slide change, please. And any model, you have to be, one of the things which is of interest to the public is how accurate are our predictions. As you can see here in this plot, you have our baseline, which is in the form of a black line, and the confirmed active cases as reported by the Johns Hopkins website. So we can say that it is a very accurate forecast which we are doing. Slide change, please. So here, I just want to present some preliminary analysis, what we have uncovered from March 1st to till April 10th, I would say. So there were 3 phases, we can say. First phase is from up to March 16th, when there were limited testing in place across the United States. And so the epidemic was just going on increasing. And then you had phase B, where you had a ramp up in testing kits and social distancing being implemented. And then you can see a decrease in the active count cases. That is the y-axis. That is because of the effect of social distancing. Okay, slide change, please. So this is the projection, what we made between the phase, between initial phase when testing was not widespread. And what we found is that based on the data till March 17, the epidemic peak would have arrived in different states between May 15th and August and July 1st, after which it would fade away. But that quickly changed upon the increase in the number of testing and social distancing. Slide change. So this is the phase B, and phase B, we were faced with a different sort of challenge, which is, okay, now that the number of COVID active cases has been increasing, what is of most interest is how this is affecting the hospital and ICU bed demand to supply ratio. And on panels A and B above, you can see the nationwide hospital bed demand to supply ratio. It is really high. And from panel C through D, you will see that what would be the effect of different social distancing measures in reducing this demand to supply. And as you can see that, of course, business closure would have the highest impact, but that is not a very feasible long-term solution. If you were to have a school closure, business closure, and distancing of elders, because the age group is most susceptible, all in effect, you are going to significantly decrease the demand to supply ratio depending on the intervention strength. Slide change. So from April 1st onward, when the effects of social distancing are being tested, are being seen in effect, we have been grappling with the research question, how long and what cost benefit does the United States need to implement social distancing intervention? And this is an interesting research question where you can see that on panels A and B, what should be the ideal or optimal implementation time of different social distancing schemes to get the maximum benefit in terms of demand to supply ratio. And panel C is the most important one, in which you will see that social distancing duration increases exponentially to bring about a reduction in medical demands linearly. So to put in perspective, you would need ideally 8 weeks of social distancing to only bring about a reduction in medical demands by 20%. So the question still remains, how much time can the country undergo social distancing to balance its medical demand to supply? So this is what we are right now researching. Slide change. So this is my final slide. If you want to read more about the details, we have 2 papers on medRxiv. You can go to the preprint server and just type my name. You will see these 2 papers. They are undergoing review in journals as we speak, but these things take time. So medRxiv has been the primary place to deposit immediate findings. Thank you.
Okay, Rich, you're on next. Rich, Professor.
Thank you, Pratim. Hello, everybody. My talk is going to be a bit different than the others. I'm going to be discussing what we've been doing at Washington University, specifically with the case faculty and staff, to guide the question of how to deal with the shortage of masks, the surgical masks or the N95 masks. And this has become a particularly important issue. Probably most of you are aware of it, but the fact that whereas in the past, these masks were really used by primarily healthcare professionals, now the public is interested in having these masks for their own safety. And this put an enormous burden on the community to supply these masks. The supply can't meet the demand. So right now there's a challenge in terms of supplying the appropriate masks to the healthcare professionals. If we look at the next slide, this actually occurred just yesterday, came out the news that in Santa Monica, the hospital in Santa Monica, actually, the nurses refused to work because one of the nurses actually came down with the COVID-19, and they are not receiving what they feel is appropriate protection. Many of you are probably aware of the term N95 mask. And so the concern here is they are not getting N95 masks. If you look at the masks they're wearing, these are what would be called surgical masks. And so here, their perspective is that the surgical masks are not satisfactory and they would like N95 masks. So a lot of what I'll be talking about, my talk has changed a little bit because I think it's just more relevant to us to understand just masks, a little bit about masks in general. Number one, because we understand what we're doing to help the medical community, but also because it's actually very relevant to all of us, because we all have the question of, do we wear masks? What type of mask do we wear? So understand a little bit more about masks, how they function, will help us to make good choices during this critical time. Okay, so let's discuss a little bit about masks. And the key point we'll talk about is the N95 mask versus the surgical mask, with the recognition that the surgical mask is a little bit more like a homemade mask to some level. It's a sophisticated homemade mask compared to N95 respirator. So the term respirator is really something that's worn. If you look at the top line, it's a critical statement. The N95 respirator is worn to protect the wearer from inhaling hazardous particles. Okay, so when someone puts on an N95 mask, they are protecting themselves. Okay, so now you've seen this type of mask before. I have one here. And you can see that the shape of this mask is, it's almost a hemisphere. Okay. Now, and you can see on the lower right, a person wearing that mask, and this hemispherical filter is sticking outside of your mouth. Okay, let's go to the next slide. And this is the surgical mask. Notice the first line, worn to protect patients from the wearer's respiratory emissions. So in other words, if a surgeon is operating, they don't want anything from their mouths entering into the wound. So the surgical mask was developed to protect the patient from the surgeon's emissions. And you can see the structure of the surgical mask is completely different than N95. It's just almost like a thin sheet of material. There's no structure to it. And when you put it on, it sort of, it sticks to your face, but not with the level that the N95 is adhering to your face. Okay, so what I'd like us to do right now is to do a little experiment. Okay, so I'm going to ask you, and I would like you to do this because I think it's very important to appreciate this. It's not just for understanding the issues of social healthcare, but actually for yourselves. And I'd like you to put your hand about 1 inch in front of your mouth, like this, and then breathe out relatively rapidly. And then breathe in. Okay, now do the same thing and put your hand about 2 inches away Breathe in. And now put your hand right up against your mouth and breathe out. And breathe in. Okay, so what you're experiencing right now is, what we understand in engineering is we have momentum and we have forces and we have Newton's law. And so we're looking at fluid flow. And so in one case, when we're breathing out, we are actually have momentum that pushes the fluid straight in front of our mouth. When we're breathing in, there's just a pressure drop. We're causing low pressure on our mouths, and the air comes to us from any direction. There's no momentum associated with the air entering our mouth. Okay, now this concept is really important because now remember, if we go back one slide, we're talking about the respirator is being worn to protect the wearer. So that's somebody who's inhaling. The person inhaling does not want to inhale hazardous particles. So inhalation and the dynamics of inhalation is critical for the respirator. Okay, if we go back to the next slide, this is the surgical mask. This is associated with somebody exhaling or coughing. And that is protecting not the wearer, but the individual from exposure to emissions from the wearer. Okay, but you saw the dynamics of the flow are completely different. So these two designs, as simple as they are, have developed over the last 100 years, really. The respirator came, we actually owe gratitude to the coal industry for developing the respirators that we use today because they needed them to protect the miners. But these have been developed extensively over time. And one of the very important things, if you go online, you will find every day some group has met with a 3D printer and they're coming up with a new design for a respirator. But the problem is these designs, if we go back to the N95, the thing that is very important to realize is this respirator, as simple as it looks, it is extremely sophisticated. And sometimes these designs that look simple are a little bit dangerous to the novice because anybody thinks they can do it. But in fact, this simple but elegant design does a lot in a little space. And so we're going to talk a little bit about how it functions because there's enormous desire right now, for very good reason, to develop methods of producing N95 masks. But unless you appreciate the beauty and simplicity and the importance of different functionality of this mask, then we're potentially going to be developing masks that really do not work appropriately, and then that's putting people at risk. Okay, so let's go forward a bit and discuss just a bit about respirators. So there's two main goals. Remember, the respirator is the N95. This is the one that's going to protect the healthcare provider, or if it's us, it would protect us as well. But the two main requirements for an effective respirator. One is it has to filter particles. That's the one that we all assume is so. But the important thing is it has to filter particles in a way that covers a very wide range and a wide range of flow rates. But an important thing about a respirator too is you have to wear it. So it has to filter these materials without a large pressure drop, because if you have to suck really hard each time you take a breath to get that to filter, then it's not working well. Okay, so it has to be able to filter under these conditions without a large pressure drop. But in addition, it has to be able to avoid leaking around the edges. Because remember, when you're inhaling, there's no momentum. So that means that the flow is going to take the path of least resistance to a T. So if you leave an opening in this mask, the flow will go through opening, because it's a lot easier to go through the opening than it is to go through the filter. So leakage prevention is critical to this mask. Also, a common misconception, and this the aerosol group knows, but many do not understand this, is that filters like this for fine particles, the aerosols, are not like sieves. They're not like a screen that's taking anything larger size doesn't go through and the smaller size does. That's not how they function. They're very small particles. It's not, the mechanism is not that. There's different mechanisms. Without getting into details, there's impaction where the particles are moving with a certain velocity and they hit a fiber in the mask. There's diffusion, where the particles are really wandering around as they move through the system and then attach to the fiber. And there's potential, if there's charge, that electrostatic attraction as well. But the general designs of the filters are designed to not depend upon electrostatic attraction. They're really designed to work off this inertial interception or diffusion mechanisms. Okay. Now, important thing with this is that the diffusion mechanisms, this third one, the longer the time you have, the longer the chance that this particle will diffuse and hit a fiber. So residence time becomes extremely important to the effectiveness of these fibers. Okay, so now let's talk about this question that the nurses had with respect to, are they protected with the surgical mask? Do they need N95 respirators? Okay, and next slide, please. Okay. So the respirators, comparing to the surgical mask, first of all, in terms of filtration, the respirators are tested by NIOSH, and they have to pass a minimum standard, as we mentioned earlier, in terms of the requirements, the respirator to filter particles. When we say it filters N95, I'll let my colleague Brett Williams discuss this more, but the N95 filter does not, it's a kind of common misconception, it doesn't filter greater than 95% of all sizes. It really filters almost nearly 100% in many of the sizes, but in the certain size, there's a critical size where particles can typically penetrate a filter. And even at those critical size, the smallest efficiency of any size is 95%. So majority of it is much higher efficiency than that. But these filters then are filtering out almost all the particles that are passing through it. And also, these filtrations, the methods have to work under the wide range of conditions that can exist in breathing. But if you look at the second point, there is no independent evaluation for surgical mask filter. The reason for that is because the challenge of a surgical mask filter is very small. You're dealing with very large particles. As Dr. Biswas pointed out, when particles evaporate, they get smaller in size. But when they're first emitted from your mouth, they're relatively large. They have that momentum, and they can actually, those large particles can be caught in the surgical filter rather easily. So they don't have the requirements of an N95 respirator. So that implies then they're good for protecting you from actually doing something that would harm others, but it doesn't protect you yourself. Another important point is the fit. The respirators have a fit factor of at least 100. That means that you basically have 1% of the particles outside can leak through the system. So most of the particles have to go through the filter and be filtered. There's some leakage, but it's very small. Whereas for the surgical masks, because basically, as we saw before, these masks are not really good fitting. They're just basically a sheet like this that you put over your mouth, so there's no real good contact with your face. And so in these cases, there's considerable amount of leakage. Okay, so the nurses have a legitimate concern, being that they're really on the front line and they have to be concerned about exposing themselves to the virus. You know, they're concerned about having better filtration, better mask is a legitimate concern. Now, there's just a few things in parting and this discussion. One of them is, you know, what do we have to have? If we go back a few slides, I want to just look at the N95 respirator. So what is it that why is it this design? Now that we can step back and look at this thing. First of all, we said that for effective collection, we need to have a long residence time. Long residence time means we need a low velocity. And a low velocity for a given amount of breath means we have to have a high surface area. So this curvature, this shape of a hemisphere, is to give us a very large amount of surface area to allow the velocity to be low. But also, as we saw from our test, we don't want the surface of the mask to be close to our mouth because then the velocity is going to be centrally located. So we need to have the mask far away from mouth, and that's why it actually has this shape that sits away from your mouth so that when you breathe in, the air comes in through the entire mask. So it has to be a high surface area away from your mouth. It also has to have a low pressure drop to avoid you getting fatigued when you're wearing it. What does that mean? That means it also has the low, the pressure drop goes like the square velocity, so you need to have a low velocity. So again, that means a high surface area. And also, again, it means it's away from your mouth. So they satisfy good filtration and low fatigue by this shape. Notice that the surgical mask or the mask that you would perhaps make at home don't necessarily do that because they're sitting right on top of your mouth. Okay, so this rigid hemispherical design is critical, but it's also important to the fit. In other words, this type of shape where it's rigid and spherical allows it to actually conform to your mouth, or your face very well. And since the surface area of contact is very small, the forces on your face can be very high, and that means the sealing on your face can be very effective. Whereas something like this or a homemade mask, there is no force on your face. So if there's any resistance, the flow is going to go around the mask and you lose that protection. So with this, I just wanted to wish everybody that you use your mask safely. Again, one thing I would close on this is while these masks may not, again, protect you, the critical thing of these masks and why it's important to wear them is you are protecting other people. So the critical thing is we're all protecting other people, then we're all safe. So wearing a mask is really important to do, even as a homemade mask, because you can protect others with a homemade mask. The dangerous thing to do is do not think you're protecting yourself. When you put on that mask, you're protecting someone else. You're not protecting yourself. You should still stay with extreme caution if you're in a vicinity of other people. Thanks.
Okay, Brent, you're next.
Okay. Thanks, Pratim. Thank you, Rich. Can everybody hear me?
Yes, yes.
Pratim?
Yes,
okay.
you're set.
Okay, all right. So I'll definitely reiterate on some of Professor Axelbaum's points that he made. I'm going to very quickly present some sort of a methodology development and some initial results that we're seeing from test stations that we've set up as part of the Center for Aerosol Science and Engineering, the CASE group within EECE in the McKelvey School of Engineering. So before I talk about the work that we're doing right now, this COVID-related work, I just want to point out the folks that are actually in the lab doing the work. So I want to highlight Ben Comfer, Audrey Dang, David Dhanraj, Shruti Chaudhary. They are the four folks that are every day in the laboratory that very quickly, rapidly set up test stations to test different masks and different filtering materials. And there's been a huge collaborative effort across different CASE faculty, some listed here, and also other students in CASE that aren't mentioned right now, but in due time, when the dust settles, we'll acknowledge everybody for the different consultation that you've offered and assistance in data processing and things like that. And then finally, I want to sort of mention that this group is also a larger collaborative effort where we're working directly with the Med School, Sam Fox School, and others across McKelvey Engineering to perform these tests and to sort of prioritize what questions need to be answered. So with that, I'll jump to the next slide, which specifically lays out some of the main questions. And it looks like they're all labeled #1, so they're all top priority. Can we help to inform on possible solutions for the following needs? So this kind of goes back to some of what Professor Axelbaum was talking about as well. So we are interested in, there's been discussion of N95 mask shortages, and they're certainly being rationed already across our med facilities. So could we help to inform on other materials that could be used to produce N95 quality equivalent masks? So that's one sort of category of questions that we're after. Also, in this shortage of N95 masks, there's an effort to sterilize masks and reuse them. And that brings up questions about how good are they continuing to capture particles? Also, how stable are they in terms of, at some point, do the materials start to sort of degrade and fall apart? And then the last thing is sort of these low-tech mask designs, build, things that you could produce at home from things that you find, local to you. Again, these are not the N95 type quality masks that protect you from inhaling, as Professor Axelbaum was mentioning, but this is more to protect, to make sure that you don't spread anything from your sort of exhaled larger particles. So with that, we'll jump forward to the next slide. I just want to start with some of the testing challenges that we've, in the course of a few weeks of setting up these stations, we've come a long ways, and we're much more confident in our data today than we were even a couple of weeks ago. But just to reiterate, Professor Axelbaum talked about this and Professor Biswas at the beginning. Small and large particles are captured by different mechanisms. I highlighted diffusion and impaction here. Small particles have a much higher diffusion rates, and so they're captured more through a diffusion mechanism. Also, electrostatics can play a role in the smaller particles, and the big particles are more so captured by impaction onto perhaps a filtered fiber. Also, interception was another mechanism that Professor Axelbaum highlighted there. But there's sort of a gap between small particles and big particles that are more of a challenge range. That this has always been the case for filtration and developing filters for different purposes. Sort of in that range of 100 to 500 nanometer particles. It's kind of a gap location where none of these mechanisms are most efficient in that range. And so when we go back to talking about N95 masks, which Professor Axelbaum was talking about, the NIOSH standards that certify something as N95, they're saying that specifically at the particle size of 300 nanometers, kind of in the middle of that challenge location for capture, particles at 300 nanometers are captured with greater than 95% efficiency at 300 nanometers. And they do designate a specific flow rate, 85 liters per minute. This is, there are some things we could challenge with setting just one flow rate, because it comes back to, actually, it does matter how big of a mask area you have, and as Professor Axelbaum was saying. So you could convert that to sort of a typical N95 mask area and actually look at a phase velocity. So that would be sort of in the range of 10 centimeters per second for a phase velocity. And as you slow that down, that can improve your collection efficiency, especially for the smaller particles that have more time to diffuse to the fibers. And we can't really slow that down by just trying to control our breathing rate. Our bodies react to however active we are. So one thing you can do in the design is try to make a larger surface area to slow the velocity down. So with this testing, we're not exactly sure what the final designs are if we're just testing material. So we test a high flow rate with velocities around 10 centimeters per second. And we're also doing all of our material testings at a lower flow rate, 4 centimeters per second. And so if I say high flow rate and low flow rate, those are sort of more so getting at velocities. Okay, so yep, yeah, next slide, thanks. Next slide, please, Pradeep. Thanks.
Yeah.
Okay. So we do have 2 test stations set up in the case across the case labs. The first one is located in the Biswas AAQRL lab, and the other one is located in the case shared facility in Green Hall. We're utilizing a lot of the similar equipment, but the test stations are set up in 2 different ways to sort of complement. Both have some strengths and weaknesses, and they complement each other to be able to have both testing stations available. Both can look at individual punches of filter material if we're looking at doing materials test, or both can be situated where we test full mask on 3D printed mannequin face. the test station number 1 is doing a full size distribution scanning of particles. And so you send a distribution of particles at the filter material. And then on the back end, you do active scanning across the different size ranges. So you can get really quick size distribution, full size distribution cycles on material. And this testing station allows us to get through more materials faster and across kind of a more complete size distribution. The other test station is actually doing size selecting particles before you send them at the mask, and then doing kind of more statistics on a specific size range, specific size range particles one at a time. And the advantage of this is we can kind of get decrease our uncertainty quite a bit, and we also don't load the filters so fast. So you have more time to work with an individual material. So next slide. I'll kind of show a flow diagram of each of these. This is the test station number 1, where we're sending an entire size distribution through a filter, and then you rotate between bypass and the filter itself, and look at the ratio of the two to compute collection efficiency. There's different size scanning equipment here. So there's some equipment that focuses on the smaller size range, and then some equipment that looks at the larger particle sizes. And the next slide. I won't go through this in detail, but this kind of talks about the types of particles we're using, size ranges, flow rates, concentrations, and overall procedure. But this is a first look example at, this is a Halyard H500 material. This is actually material that's used to make like hospital gowns, the blue kind of fabric that you see on hospital gowns. So this is a material that is a decent, in terms of something that's a cloth material, collects quite a bit of particles, but you can see here we're scanning from 200 out to 600 or 700 nanometers or so. And you can see kind of a minimum in the mid-range there for the collection efficiency. Okay, I'll come back to show some more data here in a minute if we go to the next slide. This is the second test station. So there is a DMA, a differential mobility analyzer, located upstream of the filter, and that's what's using us. That's what we're using to pre-classify or size select a single particle size at a time, and then we do the same sort of procedure of switching between the bypass and the filter, and then count particles on the back end of it, where we're only looking at one size particle at a time. Next slide.
Yeah.
All right. So here's a comparison from the 2 different test stations looking at that same Halyard material. So you can see the full size distribution from test station number 1, and then 4 discrete sizes for the test station number 2. So what we've kind of, over a few weeks of doing tests, we've kind of found that test station number 1 is good at doing a survey of a lot of different materials and comparing sort of lower quality filtration and higher quality filtration to kind of see, to get a quick look at how different materials are behaving. Test station number 2, we've started to use more and more for the N95 type questions because we get really good statistics at the higher capture efficiencies. Okay, next slide. So here's an example from test station number 1, looking at a number of different materials, everything from things you'd find in your home, like a pillow cover or a bandana fabric. The MERV material is HVAC filter material that would be in your home filtration system. And then looking at doing things like putting a Swiffer material inside of a bandana, for example, and all of this in comparison to an N95 fabric at the very top, where you can see you're always above 95% efficiency across all these size ranges. And next slide. This is a quick look. I'll be focused on the right side of this figure. This is the instrument that scans for the larger particle sizes. There's a little bit of a data gap there. But you can see that even these lower quality, some of the lower quality solutions for the big particle sizes do a decent job of collecting a lot of the bigger particles. So that comes back to Professor Axelbaum's point of even if you're wearing these materials, bandanas or whatever it is, over your face, you're still protecting others in case you might be infected and you don't know that you're infected. Okay, next slide. So I'm just going to look at a couple of the questions, specific questions that we're out to answer with our collaboration team. Could we come up with a combination of materials that perform as good as an N95 mask? And so here's one example where we're looking at a couple of different material combinations. So on the left figure, we started with the halyard material, the gown material. And a single layer of that had something like 65% collection efficiency across these size range particles. If you do a double layer, then you're above 80% collection efficiency. If you sandwich a piece of HVAC material between two of those layers, then if we focus on the 300 nanometer, which is the NIOSH size, we're above, getting above 90% collection efficiency. So we're still not there at 95% was our kind of answer with this specific challenge, but you can see that using a combination of materials does get you closer and closer. And but it's N95 it's a pretty high standard. They spent a long time developing that material, so we're still working on solutions for that. Okay, next slide. Another question was, they're starting to sterilize and reuse N95 masks that are out there currently. And one of the methods, the main method that's being used currently is the vaporized hydrogen peroxide treatment. So basically you sterilize using vaporized hydrogen peroxide. And our question was, after a couple of these cycles, is it still filtering material? And without specifying the details here, all of the untreated and treated masks are performing above 98.5%. So we're still well above the 95 specification for treated masks as well, which is a good indicator that the treatment method could actually work. Okay, yeah, next slide, thanks. The last thing that we're also interested in is, as these masks are treated over and over with more treatment cycles, do the masks themselves start to fall apart? And so we're looking at actually fiber release that could come off of a mask, and testing is underway for this. But we'll basically attach one of these N95 masks to a mannequin and pull air over it, and then collect on SEM grids. And you can see that on the next slide. And in fact, we are seeing fibers coming off of the mask. This was one case where over 20 minutes, we had 11 of these fibers that we counted. If we go to the next figure, if you agitate the mask, over the same collection time period, we had about double the number of fibers. And this was with the treated mask. We're in the process of comparing this to untreated masks. And then we'll also look at masks that have gone through even further stages of 5 or 10 or even more VHP treatment processes. Okay, so that's just kind of an example of some of the questions that we're trying to answer, looking at different materials, looking at different mask designs, and looking at the stability of these as we try to go through sterilization and reuse procedures. All right, that's all I have.
Okay, we are running out of time, so I won't go into this pharmaceutical. If you're unfortunately a COVID patient, there's a lot of work from our colleagues in the School of Medicine trying to come up with drugs. Aerosol techniques can be also used to deliver these drugs. And just to recap this, and you want to deliver a drug which will make a viral nanoparticle completely ineffective in causing infection, right? So not to be infective. And one way is that detailed arrangement of those proteins. It's a very elegantly self-assembled structure. You want to sort of break up that self-assembly. That's the strategy. And then in terms of delivery, I bring back this something that's now causing infection. I want to use effectively to deliver drugs so it can go and associate with the viral nanoparticle and do its job. And very quickly, this is from the literature. This is collaboration now with colleagues in biomedical engineering and also in the medical school. There are specific antivirals that they have developed, but understanding the mechanistic pathways are extremely important. So the strategy is to deliver the pharmaceutical compound at the same location where the virus might be. Again, a detailed understanding of aerosol physics and transport is critical. You then want to understand this assembly of these structures and sort of de-assemble it. It's known as protein denaturing, or you don't want it to replicate. So essentially you want to understand the pathways and sort of put a stop to that, right? So that's the strategy. I'm going through this very rapidly, and we would like to sort of summarize now. And this virus is a tough nanoparticle. I like to call it a tough cookie. It's not like our common cold coronavirus, which infects the upper respiratory tract. This thing is going deeper into the lungs. It's a mutant hybrid. People are still trying to understand this. So what do you really do? We want to end with this. You want to stay away from people, right? Physically distance. How far? Maybe some of the things you've heard about today will tell you how far. Of course, the further away, the better, as Professor Axelbaum also referred to. You wash your hands often. We didn't talk about this. These particles deposit onto surfaces. They're all over. They seem to have a lifetime of its own. So you don't want to pick it up on your hands. And then you want to wear masks wherever you can, even if they are homemade. And you heard a lot about that, so I won't repeat it. You want to maybe save the N95 for our frontline workers, because they are just on the, looking at the patients. You saw some data from patient rooms where we are getting large spikes of this data. And then always be supportive of people who are doing basic science and engineering research to eventually develop vaccines and antiviral drugs. So with that, I'll pause. I don't know if we have questions. Let me see. How do I go to the chat room? I hope there are some questions. Sungyun, can you see any questions?
I just sent you the text with the summary of the questions.
Okay. I will. Yeah, there are a large number, but if my colleagues are still up to it, we are happy to try and answer some of the questions. So one is, this entire presentation has been recorded, so we will post it on the website. Let me see if I can, and my colleagues can try to read some questions too in the chat section. Let me go up to the top. So I'll give it to my colleagues first. So Rajan, your website, we will circulate that. That's not an issue. So Brent, maybe you could answer this. What type of particles are being used to test the mask materials? Hey, Brent, you could come up.
Yep, I'm here.
Okay, go ahead.
Yeah, so it looks like some of these questions are answering themselves in the chat window, but I'll just talk to that. So for the smaller size particles, both stations are using sodium chloride particles. And then in the AAQRL station, where they're testing some of the larger particle size ranges, they're using a standard material that's the Arizona road dust that's being resuspended for big particles.
Great.
I had a couple of private messages about testing at high and low flow rate, and I want to reiterate that at the high flow rate is more of a challenge for materials, because there's not enough time for the smaller particles to diffuse and be collected. So materials that perform well at high flow rates so far are materials that existed for some sort of other filtration specific use anyways, like HEPA filter material or HVAC material. or N95s themselves perform the best at those high flow rates.
Okay, so this question is for Rajan. Does the time delay, in brackets, time period between the infected time and reported time affect your results in any way?
Yes, excellent question. Unfortunately, I cannot read the name of the questioner, but yes, in brief, we track a parameter called as the documentation ratio. So if you go to our website, you will see a tab called model, and there is a parameter eta, which is the documentation ratio, and this parameter takes care of this delay. What this implies is that you have the people who are infected but not reported. We term them as asymptomatic population, and we actually track that population, and that is one of the uniqueness of this model. So the unreported active cases is what we track.
Good, thank you, Rajan. Audrey, David, thank you for answering on the chat. But Brent, another question. Can we sterilize the N95 filters at home? Can you suggest an efficient way?
I can't really suggest that. The process that's used is highly controlled for the vaporized hydrogen peroxide. There were a lot of things coming out in the media about basically discouraging people from trying to wash your N95 mask at home. So I'm not aware of a good home remedy. Other than the VHP process, there's also an ultraviolet radiation treatment as well, and that's also something I wouldn't recommend at home either.
Right. So you have to be, I'll add to that, be very cautious about this, because UV light and all could have other side effects. Some people use their ovens, but I would not recommend that because we're also cooking in our ovens. So it's best to maybe not reuse filters at home or be very cautious about it. Maybe I'll go to Rich. Rich, you talked about N95. Someone was asking, are there many types of N95 available in the market? I presume you have no stocks with 3M. That I'm just kidding here. So do you know about other N95 type material or available?
The N95 is the actual respirator itself. There are other respirators. There's a KN95 that satisfies China's requirements. Each country has their own requirements. So the KN95 does satisfy China's requirements. There have been some challenges with those in terms of fit. So I don't have a recommendation right now that can say definitively it's an alternative to N95. One thing I should mention, there was a private chat that I think brought up an important point that I would like to clarify. What I did is I showed the differences between the N95 respirator and a surgical mask. Now, there have been studies that have compared the N95 to surgical masks and showed that the efficacy of the two was similar. There was no non-inferiority in terms of the surgical mask over the N95. So there are cases, we saw that, as Dr. Williams showed, the size of these particles is very important in terms of their collection efficiency. So it is possible certain viruses that actually are the particle size distribution that those viruses are contained in are collected by a surgical mask. So one critical point is my comments are not made to suggest that it's not possible for a surgical mask to be effective. The issue is it's inappropriate to assume they're effective without proof. So in this case, since we have a new virus, that we would really want to ensure the efficacy of the surgical masks before we would rely on them.
Great, thanks, Rich. So there's a question from Matt Thomas. It was recently reported in Nature that MIT was attempting to use phantom cameras, I guess very fast speed cameras, to visualize sneezes and coughs. Having used these video cameras, I have questions about their resolution. If resolution is sufficient, though, how would such information support the general modeling? I'll take a crack at it, and then if any colleagues want to. These cameras are very effective in terms of mapping the flow or getting information. But as you saw, the eventual droplet size would be rather small. And this is where we come in with our very effective instrumentation. Of course, there sometimes could be bulkier. You heard about the differential mobility analyzer, the scanning mobility particle sizer. We can go down to a few nanometers. So those are very effective in giving you the distribution by size quantitatively. The cameras are also useful. They can give you information at the initial sizes of the droplets. And the New York Times actually reported some very elegant visualizations of these. But as the droplets evaporate and become smaller, or if they start off small in size, you're not going to see them with these cameras. But the combination of the fluid mechanics, the aerosol dynamics, I'll just use that term, will allow us to then study this. Okay, there are individuals tuning in from India. So a question from India, maybe Rajan, you might answer. When you did the modeling spread, did you account for the fomite pathway, which means from the surfaces in your model? Is it as detailed? Will that help in your predictions?
So this is a population balance modeling, and we do not go down to the granular level of spread or the modality of spreading. So we do not, so that is encountered for in the active and unreported case counts, but we do not go into the causality of spread.
Okay, great. Thanks, Rajan. Another question came up. If the virus affects the alveolar region, deeper portions of the respiratory tract in the lung, how exactly does it get to ride on the droplets expelled when coughing or sneezing? This is also a very good question. So they start off, as I was trying to show, inside the droplet, right? And it eventually comes from the mechanistic details of getting into the mucus region and then ultimately into the phlegm, and then you're coughing it out or breathing it out. So it's initially in the droplet. As the droplet evaporates, it's still a carrier. As I said, the virus has to remain viable, right? And if it dries out completely and is there for a long time, it's going to get denatured and won't be effective. It might still have remnants. There's also a salt coating. This particular virus has several protein coatings and a lipid coating, which might keep it viable for longer times. But eventually, these ones would then, once it deposits in the lung, there's a transport pathway, right? They have to get into the cell and things like that. Those are details. So, so it's a complex pathway, and one has to work these answers out, okay, or develop a detailed understanding. And some of this is very topical in terms of research being done. I don't know, colleagues, speakers, did I miss anyone's questions? Or
I think there's two more questions related to the ESP. So two people about as if it's possible to cure.
Okay, so the question is about ESPs. These are room air cleaners. So we all have air cleaning systems in our homes, at least in the United States. We have filters. If you have a high efficiency air cleaning system, you might have an electric electrostatic precipitator-based filtration system. Some of these are very effective at not only trapping dust particles, viral particles, which could be very small bacteria, but also inactivating them. So in indoor environments, there's a lot of research underway to design air cleaning systems. So if we are going into a patient viewing room, I would want to have a very effective air cleaning system with a high circulation rate. So there are several of these available, and mainly in the Asian countries, they were trying to see this. People were trying to see if they could put these in their homes and so forth. But or maybe it's better in a grocery store or in a mall or a public area that these might be more effective, an airport and things like that. And okay, again, I'll put out a call. Did we miss any questions that you're seeing? If not, any closing comments from my colleagues? We are at the 12:20 mark. I noted there were more than 200 individuals. So I would thank you all for listening in. Thank you very much. And please visit our website, and there'll be additional details. And we will also post a recording of this. I think some colleagues asked if the slides would be available. I'll post a PDF on the website too. So thank you very much, and we will now just sign off.
Bye.
Bye. You can see the numbers dropping off.
Pratim. Hi.
Hey, Pratim, are you still there?
No.
Hey.
Pratim. Okay.